All right, welcome to the final project. So in this project, we're going to put everything we've been working on together all semester. We're going to be creating a linked list, and we're going to use generics, and we're going to use classes, basically loops, basically everything that we have been working on all semester. This is the time where we get to put it all together in a very large project. So this project is very difficult. You have several weeks to work on this, so please don't put it off to the last minute. It takes a lot of time to wrap your head around, and it's going to take a lot of work to kind of work through things. You might have to work on it, 3 or 4 days in a row, to where you work on it and then kind of let it rest, and then pick up the next day. So you are given plenty of time to work on this. This is definitely not a project that you can fit in one sitting. So please get started ASAP so you can take advantage of the tutoring help in the lab. And so if you get stuck, the GA can help you. Though that being said, let's go head off, and first we're going to diagram out the list. Then we'll go look at the code. All right, let's get started. Okay, so let's draw out how to use a whitelist. I think drawing it out on a whiteboard definitely helps out. So here, let's go over the add function. So first of all, we have a head reference variable. This reference variable, okay, initially points to null. Okay, when we call list.add, and then say we'll just add a string. All right. What that does internally is that creates a node. Let's use a different color here. Creates a node. Okay. And a node is just a class. And it has the data, right? So we add B, so it has the data. And then the node has a next pointer and a previous pointer. And initially, the next pointer points to null, and the previous pointer points to null. Okay, and then what happens is the head pointer, the head reference variable, is updated. Is updated to point to the new node. All right, and then this will be index 0, and our list size will now be 1. Okay, so that's add. So if we go list.add C, okay, so now we have 2 nodes. We come in here and we'll have a new node. And in this case, we're going to put the node at the front. And that's just convention. This is not like a rule, just how we're implementing our list. New items always get added to the front of the list. And then what we got to do is when we add the new node, so here is C. We have a next and a previous. And now we have to update all of the pointers here. And this is where it kind of gets tricky. So we have the head. So we want to update the head. Let's get a different color here. We want to update the head dot previous to point to the new node, right? So in code, that would be head dot previous equals new node. Okay, so now we would have this set up, right? Where now head points to our original node and previous now points to our new node. Now we want to update this pointer, the next pointer of our new node, to point to our previous or our current one, right? So we want that set up. So what we want to say is we want to say new node dot next equals head. So now we have that set up. And previous over here of the new node already points to null, because that's the nice thing about Java is Java initializes those pointers for us. And this next pointer stays at null because it's still at the end of the list, right? So the end of the list is null terminated, and the front of the list is null terminated. So we always know where things are at. And finally, we need to update the head pointer, because the head pointer is now not at the head when it's now pointing at the tail. So we need to now update the head to point to here. So now the head is now and then also ends up updates the indexes, right? So now this is index 0, and then this index 1. So this is really just it's kind of similar to operating an array, except it uses a node structure, right, instead of an array. So remember, for 121, an array is a contiguous set of memory, right? Right. So this is an array. So we have index 0, 1, 2, 3, 4, and it's contiguous in memory. There's no pointers here, right? There's no pointers. And so if we were doing an array, then we would have, B and C. Okay. So this is add. So let's go ahead and look at remove. Actually, let's just get rid of this. Okay. So let's set up 3 nodes. So I have my head pointer, and I have 3 nodes, A, B, C, and I have a next pointer going to null, a previous pointer going to B, next goes here, previous goes here, next goes here, and previous goes to null. Okay, and then the head points to the first. So I have index 0, 1, 2. Now let's say I want to remove index 1. That's removing something in the middle. So I have basically 3 cases. I have the first case is I'm removing index 0, which is the head. So if I'm removing index 0, that's a special case on a null terminated, because I need to update the head pointer to point to the next index. Okay. But in this case, let's actually go over removing something in the middle, because that one's probably the most interesting. So let's say we want to remove index 1. So we want to remove this node right here. Right here. Okay. All right. So we have a reference to the head. We always have a reference to the head. So if we want to get rid of this node right here, okay, we need to basically just unlink this node from the list. So if we follow the links down, we have head, okay, dot next, right? This link right here, we want to change it from pointing to index 1. We want to change it to pointing to here, okay? And so this goes away. And then the index 2, we want the previous, right? We want to change the previous to point here. And then this goes away. Okay. And then we also want to null out this link right here and this link right here, so that next and previous both go to null. So once we do that, index 1 is going to be consumed by the garbage collector, right? Because you see it has no references. It has nothing. Nothing is pointed to it, so the garbage collector is going to come and get it. So the garbage collector is going to come around and completely delete it, And when that happens, right, so the garbage collector is going, yum, 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 garbage, garbage, eat. And the garbage collector is then going to, once the garbage collector is done, we are left with this setup to where now we only have 2 items in the list. Index 1, index 0, and index 1. Next points to the next list, previous points to the previous, and you have null, and head still points to the front. So now we have a updated linked list. So that is that's the diagram of what we're doing. So now all we got to do is translate this diagram to code. And it really does help to draw it out. So let's go ahead and, okay. So let's go ahead and do another example. All right, let's say that we have just one item in our list, data A, or say it has, let's make that's a little bit sloppy. Let's try it again. Okay, so we have one node. Having one node is actually kind of nice, because that means next goes to null, previous goes to null, our head pointer goes to here. So here, this is kind of cool, because we just, in our list, we just say head equals null, and that gets rid of this connection. And when that happens, the garbage collector, again, null, the garbage collector then comes in and gets rid of that node. So we're not back down to nothing. All right, so now that we kind of got a visualization, right? We have a way to, we have a way to kind of visualize the nodes, right? So we have a head pointer, we have a node, and this is an inner class, then we have a list, right? Those are the 3 things we're dealing with here. The nodes are where the data is stored, and we have some data, right? This can be strings, it can be basically any type of object. Then we have next and previous pointers that point to the next node and the previous node in the list. The list maintains the head pointer, right? And it initially just points to null, right? And that's pretty much it for a linked list, a node-based linked list. The nice thing about this is a fundamental data structure that can be used to build a whole bunch of other data structures. Some of the stuff that you've learned about in this class, right? This linked list can be used to make a stack. It could be used to make a queue, right? It can also be used in other data structures like a hash table, because it can, if you're doing a hash map and you're doing chaining, the chain can be just a linked list. So it is extremely powerful and good to know. So now that we kind of got a basis, let's go take a look at the code. Okay, so as with everything, let's go take a look at the tests first. So here we are in my list test, and we have a set of tests to kind of ensure that our list is working, and also kind of to show how our list looks from the outside, right? So we declare a new list, and we're using generics here, and we're declaring our list is holding strings. Okay, so my list of type string. So I have my list equals new my list, and I'm using strings. Okay, and what I want to do is just I want to assert is it empty, because like when I make sure the list.getSize is 0, because when I make a new list, I would expect it to be empty and not return like 1 or 2 or what have you. Okay, then I have a very quick test add where I open a new list. Right, I add the string hello, I add the string world, and after each add, I assert that the size is actually increasing, and the size is increasing, and that the list is not empty. Now, you notice one thing here that I'm not doing in this add is I'm not actually testing that the data was actually added, because I could, internally I could just be, incrementing this counter. So this really just makes sure that my size is behaving as expected. Okay, so here is a more thorough test add get, right? Where I add up I create a whole bunch of new nodes. Hello world foo bar. Now internally, because every time I add, I'm adding right to the front of the list, that means that the first one added is actually the last one in the list. So internally, my list should look bar, foo, world, hello, because bar was the last one added, then we added foo, then we added world, then hello, right? So this is this lines up to what we did when we drew out our nodes, right? First, second, third, fourth, because we're always adding to the front of the list. So then I go ahead and say, all right, I should have 4 items, right? Now remember, size versus index is different. We are 0 indexed, but we have a size of 4. So index 0, 1, 2, 3, but we have 4. And I know it's really confusing, but that's just one of the things that is very common in computer science. Right? 0-based indexing, so the size and the size and the indexes are not going to match up, right? So index 3 is the 4th element. Okay, then we can actually go through and make sure that what we got, that if we call index 0, we get what we expect. So if we call index 0, if we call get 0, we expect bar, because we look up here at our little diagram and this is bar. So we can assert that when we call get, it returns the string bar, and so on and so forth, right? So we just go through 0, 1, 2, 3, and assert that we get what we expected on our list, okay? Then we go ahead and clear the list, and then we make sure that we actually can access it, right? So, because if we clear the list and it's empty and its size is 0, we should get null, if we ask for index 1. So if we clear the list, right, and then we call get index 1 and we get something, then that means we actually didn't clear the list correctly, right? Then try accessing an invalid index. And I'm sure that there is a lot of more. This test is very minimal. There's a lot more testing that you can write on this. Okay. Then we do the same thing. So this we test remove head and tail, because removing the head and the tail is a special case, because we got to remember to update the head pointer. So this is the test that we make a list, we remove the head, we expect the list to be now in this state, and we just go and test it. Remove the tail, we expect the list to be in this state, so we test it, and so on and so forth. And then we go and test a middle, right? So we create a list, boo, far, world, hello. We want to remove index 1, so we're removing foo. That means we expect the list to be bar, world, hello, and then we make sure that is what we get. Okay. Now, one of the things we are implementing is we're implementing an iterator, and the iterator is what allows us to just iterate through the list. Like, iterate means walk through the list, right? And the iterate interface only has 2 methods we got to implement, so it's pretty straightforward. And it allows us to walk. And so in this case, we're actually just going to test the first one. So we get a new list, we declare a new iterator, and then we just call iterator.next, and we should be on bar, and we are. So now we're going to actually test an expected exception, right? So in this case, this is from the exceptions lab, right? Where our test class is actually going to, we are actually going to construct a test that is expected to fail, but we're kind of going to flip it, because we're saying, hey, we expect an exception. So mark me as pass, not fail. So in this case, I'm going to call list, create a new list, get an iterator on an empty list, and then I'm going to make sure that it's, assert false has next, then call next, and it should throw an exception because there's nothing in there. Okay, then I'm going to just do a quick test for each, because we have implemented the iterator interface. we created a list, we should now be able to use the Java for each list, which is kind of cool because then that just makes it really handy, and our list will now work in just like any other built-in list. So we can go ahead and run it. So we can say great LW test, and we should see everything pass. All right, so it looks good, and here's our iterator. So now let's go over and look at the code. So here is the interface for our custom linked list, and we're using generics. So you might want to go and review the generics chapter again. We're basically just saying this list will take any type, and we just say T. Like this T is think of it as a placeholder, right? It's something that just it's there until we declare what we actually want. If we look at our test, you can see that right here, T, we declare T as to be of type string, right? So if we look at the list, so this string gets replaced here. And so if we want to declare string, so this will be string, right? T, everywhere T is string, right? So that kind of makes more sense now, right? We add a string, remove a string. So just think T, and then actually this goes away because once we declare a type, then this is what it looks like, right? Just string, string, string. T's get turned into string. If we declare integer, right, then integer would be that, right? Would be declare it as an integer or what have you. Basically any type. That's why it's generic. So we add, and the add says just appends a specified element to the front of the list. Okay, if we have such a list A, B, C, and we call add X, our list would look like X, A, B, C. Okay, remove index is where it just removes index, so it's zero base, so 0, 1, 2, 3. So if we call remove 1, we remove, or sorry, if we call remove 1, we remove A. If we call remove 0, we remove X. Okay, get will return an element at the specified position of the list, and the key here is returning the data, not the node, right? Okay, in fact, let's actually clarify that. Returns the data, not the list node. Okay, so the list node, the node is internal to the list. We will never know it. The user should never know it even existed. Oops, not. Okay. Then we have is empty, just returns true if it's empty. Clear just removes everything from the list, and then get size returns the size of the currently that's in the list. All right, so let's go look at the actual code. All right, so now I give you a partial implementation to kind of give you some guidance on what you're supposed to do. So what it is this is my list. Again, type T implements my interface, LL, that's my interface. Okay, and then I'm also going to implement iterable, which is from the Java API, right? So you can see java.lang.iterable. Okay, now I am declaring a private inner class. Okay, so what a private inner class is just think of it as like a helper class. It is private to my list, and nobody outside of my list will know it exists or can even access it. So if you notice over here in my test, I never use the term node, right? Whenever I call add, I'm adding strings. Whenever I call get up here, if I call get, I'm getting a string. I'm not getting a node. Okay. So if we go over here, my node, now this hopefully makes more sense. Remember the drawing. I have data, right? Type T, which in our case, we were just using strings. Then I have a next pointer and a previous pointer, and it's the same type because I can point to myself. So this references back to the drawing I did earlier in the video. And then I just have a simple constructor here that this is just kind of a helper to, so it's not 100% necessary because all my items are public. They're all public because in this case it's okay because this is a private class. So the constructor is just kind of a helper code here so I can quickly construct a new node. Okay, here's my head variable as I discussed in the diagram. It initially just points to null. And then here's the size that we that stores how many numbers, how many the current number of elements in our list. Now this we could actually generate, right? We could actually just walk the list and then generate this every time. But it's much quicker just to keep it updated and store it as necessary. So I actually am giving you an entire add function. I'm giving this to kind of as an example, right? Because this is what we went over in the video. So I create a new node, right? And I think in the video I called it new node, right? I'm just going to call it n because it's less to type. And I construct it with my data. So add passes e. Okay, in this case, like if this is a string, right? Right? Because when they new it up, I pass it, and now my node is storing a string. So in the video, I used a, or b, etc. Right? But since we're using generics, right, we want to be able to do any data type, not just strings. Okay. Then just in the video, if the head is null, right, then that means it's the first item. So we just assign our node and we're done. Otherwise, we link it in, right? We're putting the new node at the front of the list. And this is helpful. I know this code can be confusing. So it's helpful to go through and draw out these diagrams, just like I did in the video, to help you understand what's going on here. Okay. And then we have, there's add. And now I have get, which gives you an example on how to iterate through the list. So I first check some special cases, right? If head is null, I just return null because there's nothing to do there. If the index is greater than size, I also return null. That means that this is where like they're at. So if I say I have 4 things on my list and they ask for the 55, index 55, well, I don't have, that's invalid. So I just return null. And if in negative indexes, okay, I return null. Now, I say we don't support negative indexes because some lists do. Some lists, like in Python, you can give -1 to say, I want to go backwards in my list. So a -1 would actually be the end of the list because you count backwards. But we're not going to do that in this. That's just too complex. Okay, and this is how you walk the list, right? So this is kind of the example, right? Which is node current, I set to head, and then I just walk the list. I just reset. I say current.next equals current. So I am dereferencing my next pointer to get the next node in the list. Okay, so that is a good example. And then right here, the remove is where you're going to implement it, right? So you're going to implement that. So let's go down and look at the iterator next. Okay, so here's my iterator, and the iterator comes right after, say, get size, right? So I just have a private class here, and it implements the iterator interface defined in the Java docs, which you can go read. It's fairly simple. It has next and next, and that's it. So when we create a new iterator, right? So this is the iterator. So when we create a new iterator, we just return a new iterator. And when we return a new iterator, we initialize the current node to the head. And this head references, that is the reference to the head of our list. So this is a class, an inner class. And when it's created, we initially have it pointing to the current node. Okay. Now has next, since our list is null terminated, we're just saying is, if current is null, that means we have no more items in the list, right? Okay, so this is kind of cool. We're returning a Boolean statement here because this expression, right, is a Boolean expression. Current does not equal null. When this expression is evaluated, it is replaced with a Boolean, which we can then return, which is kind of cool, right? And so then the next, right, this is where we're going to implement this, and this somewhere in here, right? So let's just say, like, we're going to have to hit, we have cur.data, right? Return cur.data. Now this is not correct, right? This is this is an example. This is there's more to do in here, but somewhere in here we need to return to implement need to return cur.data. Okay. So that is pretty much it. So that's the linked list in a nutshell. You need to implement the next of the iterator, and then the other to-do comments that are in this code. This class. I encourage you to go back and watch the video, the beginning of the video where I diagrammed out the list, as it could really help you out in visualizing it. Linked lists are hard. It's a difficult problem, and that's why it's important to have a picture in your head of what they look like in memory. So again, I hope that I hope this helps you out, and good luck implementing this. Please get started ASAP, because this is a very difficult project, and happy hacking.